Let me start by apologizing to my co-authors whose names didn't get on the brochure, but they've been all on 2 out of the 3 submissions I've put into the place. So there they are, a bunch of my colleagues from various places, San Diego, UC Illinois, and a business I'm running called EPIImaging LLC. This talk deals with sort of an alternative perspective on how to get 3D information out of a camera system passively for light field imaging. The requirement that, I mean, I've been in 3D vision for a long time, and it's sort of the bane of it has been that it's hard to get predictable results or, you know, perfect results and anything near perfect. A lot of mistakes because of the search involved and the likelihood of making mistakes. So we're looking for an approach that has very low error rate and high precision, can do 3D and do 3D furthermore on a 360-degree sphere, for example, and doing it by falling back on a technology I developed many years ago with some other colleagues called EPI analysis. It's a different strategy for doing multi-camera 3D. Multi-camera systems have been dangerous to work with because they've been complicated, many parts, connectors, wires, all kinds of lenses, interfaces. They tend to look like you know, multi-headed octopuses, and they act about like that, very strange, difficult, fragile, you move them around, difficult. So it gets complicated when you have lots of cameras too, that the amount of computation tends to go up with exponentially, and choose 2. So people have thought that it's kind of not a good thing to do. So the goal here was to try to develop and demonstrate technology that was simple, and the simplicity would come through getting rid of the search. So no search involved in doing 3D and passive imaging. Get accurate and reliable results, become predictable in some sense, and to be precise through ways, for example, having larger baselines without incurring a harder task of doing matching. EPI has been around for quite a while. We developed this in the mid-'80s at SRI. And it comes with a vocabulary of sorts that you have cameras arranged. Let me run this little video while I'm talking here. You run cameras along a line like this. It's an axis. That axis divides the world into a set of planes. They're called the peninsula planes. And the imaging surfaces intersect those planes here along these red lines, along these token planes. So those lines intersecting are called epipolar lines, generally. They can be in any orientation. Here they're nicely orthogonal, so they're parallel scan lines. Those planes are epipolar planes. They all pass through the axis of the cameras. You have to build it that way. It's impossible to build it that way, but you do your best, and then you calibrate. The projections in the images are epipolar lines, and the images are stacked up to form a volume that's called an Epipolar-Plane image. The lines are stacked up to form an image that's called an Epipolar-Plane image, and there's a bunch of those, for example, 1 at each scan line in the image. What's interesting is that because the world is divided up into these planes, all the information needed to process that slice in the world, and there's like n slices, is contained in those individual planes, and they can be processed separately, completely independently. And the slope of the features you see in there, this is like a single feature that's seen from multiple viewpoints. It's got a fixed disparity over camera, so it looks like a nice straight line. So those lines give you the depth. So that's the point. Now this was looked at, EPI was looked at as being sort of nice and interesting theoretically. It was the first paper in the first issue of the premier journal of our field, International Journal of Computer Vision. They solicited it back in the 80s because it was such a sort of radically different approach. They said, wonderful, but it's totally impractical. Well, things have come along to make that a bit different now. Various innovations in like smartphones and computing and architectures have made getting camera arrays going and doing all the computing to be no problem, relatively. So what we needed to do in building this was to call upon cheap, small, global shutter synchronizable sensors. Everything else is like falling in line with fast buses and multi-core, mixed-core GPUs, FPGAs, all that integrated chips. Lenses have become to get extremely good, very low cost through advanced computer design. That's been a big advantage. Wafer level integration is making sensors with lenses on them that are like a millimeter cube. So there's no reason to worry about any of these factors basically anymore. And we can sort of boldly go into the world of multi-cameras. EPI works in our processing. I'll be showing you the module and what it does. 2 phases. You first build the array, and that's a bit of work. Focusing the imagers and calibrating the system. then you sort of have locked it down and you turn it loose with the processing. The processing is a loop on rectifying images, that is bringing them into epipolar alignment so they can be worked on as a unit, constructing the epis out of them. So here's like images, there's the volume being stacked up. Here's an epi formed in that volume. There's the epi there. And then you look at the straight lines in here, and each of those lines becomes a point in the world, and you build a point cloud. So it's a pretty straightforward method here that's just a bunch of transforms and resamplings and estimations. There's the EPIModule we built. It's about 4 centimeters square, 9 images up and down. In light field terminology, this is an S axis, and that's a T axis, S&T, and they share the reference imager right here. So whatever's going on in this is going on in that, as indicated by what they both see in the reference image. So that ties them together. There's no need for this thing to be a cross. We've had L shapes and a variety of other things, triangles. They just have to share an imager, and they have to be locally straight lines, and then they can junction off into something else. There's the back side of it with a big processor. That's a Xilinx Zinc multi-processor system on chip. It's got a quad core. I'll talk about that in a minute. It's got a whole bunch of stuff in it. Here's like a test pattern. There's what comes out of this thing for range cloud data. So you see a bunch of different patterns, and all the redundancy and a repetitive pattern here causes no problems at all for EPI. I built many such EPI cameras in the past. This is a bunch of them over here, just to get an idea that there's a sort of a lineage of this stuff that goes to the current module, getting smaller and cheaper, and inbuilt embedded processing to go with it. So the module is built as 2 pieces, as the 2 PCBs, 17 Aptina 1.3 megapixel global shutter sensors with sync on them explicitly, so they all synchronized. On the back side is the Xilinx MPSoC with, what's nice about it is that you don't have to interface anything with wires. Everything is like, traces, so there's no need to have connectors, that kind of thing, which are really terrible things to be working with. The multiprocessor is a quad-core ARM, a dual-core ARM, a GPU, not a particularly powerful one, but it's OpenGL compliant, and an FPGA for doing all the interfacing, and down the road, for doing more of the computing. We haven't done much on the FPGA at the moment. That's the size of it. We're running it with the module having Linux on it. It connects with Ethernet, USB, Thunderbolt 3, and the lenses are nice and small. There's an 8 by 0.35 M 8 by 0.35 thread, quite tiny, 67-degree field of view. They're designed sort of to have a pretty steep chief ray angle, which is kind of nice. A good coverage. The sensor is about 6, so that's plenty of coverage. And the module runs at about 17 watts. So a little light bulb. Here's what it looks like. The architecture is a client server. On the server side, which is the module, it handles the cameras. It handles the application we have. A couple of methods are running at the moment. One is the structure tensor EPI variant that Heidelberg put together over the last few years, and they've done some quite interesting light field work with it. Mine's a slight variant of that, where I use zero crossings to filter and only use the places where there's a feature, not just everywhere. And then my own zero crossings, which is the original EPI work from the 80s, has been put onto this thing in a bit of a different way too. The client side is Linux and Windows both. We have an application that sort of controls the module and acquires data from it, manages and controls all the registers. One of our implementations is running on a NUC. So it does the visualization. We run the calibration there. And we use that to combine multiple modules. So you'll be seeing a little bit about this guy in a minute. That's really the desire for the collaboration with UC San Diego and University of Illinois Chicago was to get a 360 camera going. And this is what we built sort of as a token move toward that. Calibration is really critical to any of these kind of situations involving multi-camera arrays. I've been particularly concerned about that in the last few weeks when I found that, slight aging effects of the camera make the calibration go totally screwy, and you have to really be prepared to calibrate on the fly, which we're doing. We're preparing for. So here's a bunch of images. We focus by running them at sort of reduced frame rate, so we can reduce the size so we get higher frame rate coming out of it. It's currently about 1 hertz over Ethernet, which is great. We have a Thunderbolt 3 implementation, but it's not quite ready to be used. So we watch the cameras as they're looking at a pattern, and we plot the sort of the gradient power. There's some of the squares of the gradients in the image. And in different windows, we can choose that, but here's over the whole image. Where the green shows the current power and the red is the best it's ever seen on that camera. So we just have to tweak these knobs till we get the green everywhere, and then that thing's in focus. A colleague worked with me many years ago who's a professional photographer and a whiz. He sort of did the original fundamental matrix stuff, QT Long. He said this method is better than his eye. So I think that's a pretty nice way to do multi-camera focusing. It works quite nicely. The camera comes out looking like this. There's the cross. We use this as sort of a reference display. There's the S-axis, there's the T-axis, and the reference camera in the middle. Calibration, we have many ways of viewing the results from this. This shows here, that's what the individual cameras see when you, after you rectify them, but before you apply our final refinement process to it. So the centers of projection are kind of bouncing around a bit, and when the final work, everything lines up. So the centers of projections of the cameras lined up look much like they do in the module itself. They're displaced here by that baseline. So we can see that the cameras are looking good, and in the earlier case, they were kind of screwy. So the calibration is something we need to have good tools for assessing, not just numbers, but looking at what the patterns say. What's interesting about EPI and any of these configurations, be it this two-armed cross or filling in the whole density of like a 9x9 array, is that when you do the calibration rectification, one transform for each imager maps it to a common space where it can be used for all other processing. So there's none of this n choose 2 business going on. One transform and everything maps to a common space where they can be brought together. That's sort of one of the glories of this. Here's images before calibration. You'll notice there's a bunch of, I'll show you back and forth, they sort of, here's something where they don't really line up there, and you see they line up. So the calibration's job is to do this, to remove the lens distortion, to center them, to compute their pose, and combine them into this one big transform that makes them all proper for doing this EPI. Sorry, these are dark. We run at the moment with a gamma compression on the module, so we can get more bandwidth out of it. It's from 12 bits down to 8, and this process I had running wasn't really doing much gamma correction on the output side of it for looking at. So this is an EPI through about here in this image, and you can see what it looks like. So this EPI is sort of orthogonal. It's going through here. So for the reference image, it's like the middle row of this is the reference image data. This is the image, and this is actually the Laplacian. And I'll run this. You can see two things up here. What's really useful for trying to figure out what's happening with the data is to break it into the S and the T components separately. Hopefully that'll run. So these are the spatial zero crossings in the reference image. And then I'll represent them here by red and green, which are the components from the S and T on that spatial zero crossings. So it's just, the reference zero crossings are important, very important, because what they give is, let me go back one. They give the spatial structure of the image. Normal point clouds, you get like the night sky, a bunch of points, and there's no real coherence to it. It's just a bunch of points. And then people do things to that data to try to group it, segment it, to pull things out by locality. With our stuff, we actually end up with a structure description that has these point clouds put into a framework that's, in fact, they're strings. We call them string clouds. And we've evolved them into being, the next step is to evolve them into being surfaces. But it's a big step up if you already have all the points joined up by the continuity, and that comes from that. So here's the result of that imagery. You can sort of, maybe hard to keep that from inverting as a necker, but I'll run that again. So this is, you can see the point clouds there, and they're in fact represented as strings, so they're all joined up. So the localization is about 1 part in 1,000. We get that by looking at our deviations in our calibration target itself, not with any reference objects. The spatial localization coming from the use of a Laplacian in the image is about 1/30 of a pixel. I've measured this over the years, and it's pretty reliable. About 5 bits of subpixel localization for what I'm estimating. Since we're not just matching pixels, we're matching these features, we get a vastly improved definition in the scene. So it's highly localized. 5 bits of subpixel plus, in this case, 1,000 pixels across for the image. Using features, we get about 10% density, depending upon the size of the Laplacian we're using, which isn't bad. So out of a 1.3 megapixel sensor, we're getting 130,000 measurements. So, and it's only the places where you have something to talk about. I mean, most of these processes that do pixel matching just match blindly, end up with a lot of data, but a lot of it is quite spurious. So we're only dealing with features that we can localize. That's kind of important. So we Looked at all kinds of geodesics, like how do you tile a sphere with cameras? Well, you try to figure out what your field of view is, you figure out what kind of geodesic you might use. We looked at a bunch of them. Turns out the soccer ball is like good for our module. We built a module first, then tried to figure out what kind of geodesic would work for it. Turned out it's this truncated icosahedron, the fancy name for a football, a soccer ball. It's got pentagons and hexagons on it, and we chose a configuration here of these three. So this is these are the frusta from the front, and you see they overlap, and this is frusta from the back, and these are the, I can't blow that up, but these are the imager sensors right there. Looks like this, three of them facing off in different directions with a nominal amount of overlap. This is what the back of that looks like. So there's a USB, there's a 20 gigabit Thunderbolt that is it's built into the design, but we haven't FPGA'd it yet. That's still to come. Gigabit Ethernet we use for most of our stuff at the moment. Communication, heating, fan to cool it, SD card, synchronization cable so we can daisy chain these things between modules and have a master slave between them all, power connector. So that's the back side, and that's the module. Here's what, for example, this is the left and the right of that triple you've seen. So you see the three depth maps coming out of it. And down here is the composite that comes from just joining those up. So you see the two. The third one, the camera had a problem, and I couldn't make it run when I was doing this. So you get two. We'll soon have the third one back up again. So that's the kind of point cloud that comes out of this, and it's it's actually pretty impressive that you get all those data, and they're very reliable. So what I've shown you is the motivation for using EPI, its simplicity through no search, its reliability through redundancy, its accuracy through lots of observations, and you can have these straight lines and basically features that you can localize. The geometry of EPI, the spatial implications of these planes and the various lines, and the fact that you can do it now because of the smartphone wars that have given us all the gear we'd ever want for getting at this topic. Highlights of the processing, building the camera system, the specs, the communications, and about the strings. And the final thing is the module that puts together the data integration. So we're looking at doing more modeling with this, applying it to different obstacles, different applications. We had some money from NSF and a small business innovation research grant to apply this for robotics, put them in the fingertip of robots. We actually built a module that does that. We built it, but we didn't make it do it because it turned out that we couldn't get close enough with the processor with the signal. So we are going back to that with about a 1 centimeter version of this 4 centimeter camera. Other applications you can imagine, and looking at developing collaborations. Contributors over the years to the EPI technology and various versions of it that have turned up are listed here. And the two NSF projects that have funded it, one is the project from UC San Diego, Sensei, and the SBIR for EPIImaging. Okay, thank you very much.